But I'd just like to introduce Professor Chris Rapley as the director of the British Antarctic Survey, who will give our talk on polar regions. Just my own very anecdotal knowledge of Chris's accomplishments and activities. I know, for example, that he was the Secretary or Secretary General of the International Geosphere and Biosphere Program before he returned to the UK and did the world science community great service in that activity. So I'd just like to acknowledge that. And Chris, thank you very much.
Thanks, Steve. Well, good afternoon, ladies and gentlemen, everybody. Can I just check that you can hear me clearly at the back? A little wave. Good, thank you very much. Well, it's a real pleasure to be here to celebrate a great piece of British technology. There was a great debate a few years ago about whether science should be technology-led or science-pushed, or perhaps the other way around. In fact, the two things are completely intertwined, but every so often you get a piece of technology that opens up completely new windows and allows completely new science to be done. This is one of those. The UK took an inspirational lead on this. I guess the first thoughts were a long time ago, and so here we are now to celebrate what we've got, and you'll hear more about that this afternoon. Now, I've been asked to set the context, which is, as you see, why study the polar regions, something quite close to my heart. So I intend to give you a quick 20-minute gallop through the reasons why I believe the polar regions are particularly important pieces of planet Earth. And if we can get this thing to go forward, yes. We jump straight into a picture, Jim Hansen and co.'s image of the amount of warming that's taken part on the surface of the planet over the last 50 years. You can see there's been a general warming. We know it's about, 0.6 degrees Kelvin, something like that. But there are three areas where the warming has been much greater than elsewhere, about 5 times elsewhere. So that's Alaska, Siberia, and the Antarctic Peninsula, a few other little patches as well, won't go into those. And just in general, the physicists amongst you, and probably others as well, will have heard reference to and understood the ice albedo feedback, which is a positive feedback, which led people like Bodico 40 years ago to predict that the polar regions would amplify any anthropogenic gas-induced global warming, enhanced greenhouse effect. The idea being that if you've got a white surface of ice or snow, it reflects away sunlight, keeps the surface cool. If you blowtorch the snow and ice and expose a bit of ocean or land, it will absorb the heat, and you get a positive feedback. In fact, it's not quite as simple as that, because the polar regions are notoriously dark half the year, or thereabouts. And if you've got an exposed patch, it can lose heat quite effectively too. But by and large, the ice albedo effect works more or less the way it was predicted. And so at the root of these amplifications, that lies deep down as a physical process that can explain why this happens. Anyway, regardless of the mechanism, the fact is that the polar regions have warmed more strongly than pretty much anywhere else on the rest of the planet. And that has some consequences. The point being that regardless of the mechanism, if you have snow or ice somewhere near 0 degrees centigrade, a small incremental change in temperature will cause it to change phase. So you will go from a solid substance, which is sealing the surface either of the ocean or the land, to something entirely different, liquid that flows off and does something else. So if you look at the planet, and you're looking for places where something dramatic happens as a result of incremental changes in temperature, then it's the polar regions that you need to go to. And in that respect, they can be seen as the kind of miner's canary of change in the Earth system. So, amplification at the poles. Goodness, this is hard to work. Now, the animation is working, that's great. What consequences have there been of these temperature changes over the last 50 years? Well, what you're seeing there is a nice little animation which you can pull down off the web, which shows summer sea ice extent in the Arctic over this period, and the graph on the right just shows those data points as a function of time. And we know that from satellite remote sensing that there's been a 25% reduction in summer sea ice extent over that period of time, and there's even some evidence of a little bit of acceleration at the end. As I say, sea ice acts as a very effective lid on the ocean, very much reducing exchanges of moisture, heat, and momentum. And so if you reduce the amount of sea ice cover, you're going to have profound effects on the coupled ocean-atmosphere system in that region. So that's one major change that's taken place. Also in that picture, you could see the Greenland ice sheet, and things have happened there as well. The southern part of Greenland is close to this critical 0-degree temperature. And you can see in the center panel, the areas of red show the zones of summer surface melting on Greenland. The graph in the middle shows the area as a function of time. It's a pretty noisy signal, but there is a secular increase in the area. And you can see on the right, 2005, a very substantial area of Greenland surface now melts. There's a very dramatic picture on the left showing what happens to that water. It pours down cracks and holes in the ice sheet and then burrows its way underneath, where it does evil deeds like lubricating the underside of the ice sheet so that gravity can cause it to slide and judder towards the ocean more effectively. So dramatic changes in the surface melting, but also on the right-hand side, a series of synthetic aperture radar images from which glacier motion has been determined, actually by Eric Rigno and others at Jet Propulsion Lab. And so we know, again, very recent result, that the amount of sliding of the glaciers has increased very substantially over the last decade, again showing apparently some signs of acceleration. And of course, if ice slips into the sea, it can melt at leisure. And so the timescales for having an impact on global mean sea level when it's sliding into the ocean are much shorter than if it melts and then drains into the ocean. So there's a lot of new evidence that's causing a complete rethink of the contribution of Greenland in particular to the issue of global mean sea level. Now, if you put a lot of fresh water into regions of the ocean where you have significant downwelling due to the water being salty and cold and sinking, you see two little yellow points up at the top here of this nice image of the linked global circulation of the oceans. I should just back off a little bit and say that Carl Wunsch or others who are kind of real oceanographers will point out to you that there's 10 times as much energy in the little kinetic whirls of the ocean, so that they feel that this rather underrepresents the way the ocean really works. But nevertheless, there are systematic drifts in the ocean, and this picture does bear some relationship to the way that the real ocean works. And what you can see is that if we just concentrate on the north for the moment, there are some key points in this system which, if you tamper with them, can have global consequences. And we know that in the last glacial period, it's postulated sudden rushes of fresh water into this northern area changed the downwelling and therefore the global circulation of the oceans. We don't know if this can happen in warm periods, the interglacial that we're in now, but clearly there's a concern if we've got increased melting, changes in the behavior of Arctic sea ice, that this may happen. And NERC has responded to this with its RAPID program, where we're both through measurements and also comparison with models, trying to figure out whether there will be a regime shift from the left panel to the right panel with a major impact on regional climate to the east of this zone and on fisheries and indeed the whole ocean ecosystem in this area. So another big reason to worry about changes in the north. Down in the south, this is a year-long animation, an animation of a year's worth, you don't have to sit here for a year, of Antarctic sea ice melting away in the summer and then regrowing again in the winter. So this is built up from daily satellite composites. This is the biggest physical dynamic change on the Earth's surface over the year. The doubling of the size of this white blob on the bottom of the planet. Of course, the sea ice isn't very thick, it's fairly fragile. As yet, there's no evidence of the bulk of the sea ice melting back in the same way that it is in the Arctic. But in the Bellingshausen Sea, why didn't that work? There we are. In this area in the purple circle, there has been a significant reduction of sea ice, possibly not so much by melting, but by a change in the prevailing winds that pushes it a bit further south. And this is linked, or seen to be linked, with the strong warming that you saw in that earlier Hansen plot of warming over the Antarctic Peninsula, although there are other mechanisms which are gradually being understood which account for that warming too. Now, this sea ice, again, provides this insulating cap between the ocean and the atmosphere. What I forgot to mention in the case of the Arctic, but it's particularly important in the case of the Antarctic, is that this provides a substrate for biological activity, particularly for krill, and I'm going to come on to that in the next slide. This little fellow, and you can see the green plants that he's been eating in his gut there. So he grazes on phytoplankton, which in the spring grow like upturned meadows under the sea ice. And krill is the substrate of is the main substrate of the Southern Ocean ecosystem. So biologists argue that this is a fairly simple, relatively simple ecosystem. If you can understand this, you're doing fine. This is a good one to model. The complication is that ecosystem, which is biologically fairly simple, not that many trophic levels in it, is being transported by this strong circumpolar current, the Antarctic circumpolar current. And so krill that spawn under the sea ice around the peninsula, which is being affected by this strong regional warming, are carried by this conveyor belt round to the kind of Serengeti of the Southern Ocean, which is around South Georgia and to the east of it, where one has this huge intensity of seals, penguins, albatrosses, fish, all of the higher predators. Now, what we know is that there are teleconnections, both ocean and atmospheric teleconnections, from the equatorial Pacific to the sea ice around the peninsula. And a couple of years after a major El Nino event, the sea ice is reduced. That causes a reduction in the supply of krill. That information takes a little while to make its way across to the South Georgia breeding area. But when that lack of krill reaches there, all of these guys have a bad year. And you can see the curves showing breeding success of 4 higher predators. So what we know is that, if you like, 4 to 7 yearly natural cycles with teleconnections can have huge impacts on the breeding success of this Serengeti. And so, of course, one's concerned about what the secular change effect will be as this area warms further. And it's not just, if you like, a biodiversity argument or an argument about preserving the planet the way we found it, but there's a very major and economic fishery in this area, which is managed using an ecosystem approach, but clearly there are livelihoods that depend on the breeding success of the fish in this area, and indeed the health of the whole ecosystem. So this isn't just an academic issue. There are strong commercial interests in understanding how this system functions too. Right, so I've been talking about regional effects of regional warming in the polar regions, so sea ice reduction and the consequences of that, possible changes to ocean circulation and related changes to climate because the ocean and the atmosphere are so tightly coupled, ecosystem impacts, fisheries impacts in particular. Now I just want to go on to a little bit further. The warming in the peninsula is very dramatic. We have the temperature records, but we see the consequences. A study last year showed that 400 mountain glaciers along the Antarctic Peninsula, 75, roughly 80% are in retreat. Some new work, which will be published shortly, will provide some very interesting new results on the extent to which they have also accelerated their discharge and therefore increased their contribution to global mean sea level rise. And the bottom line is that it's significant. We've also seen the collapse of a number of ice shelves, much heralded in the newspapers. This is something that the media and public are very interested in. So the red stars show where ice shelves have collapsed. The green stars show where ice shelves are still in place. The beige line shows roughly what we can describe as the 0-degree summer isotherm. So at present, to the north of that, one gets significant summer melting, surface melting. To the south of it, one essentially doesn't. And the physics behind these collapses, it's all to do with the effect of surface meltwater leveraging the collapse of the ice shelves by seeping down through cracks and essentially breaking up the mechanical or weakening the mechanical fabric so that some other event, maybe a storm, maybe some sort of ocean surge, can cause them to catastrophically collapse. And the point about it is that over the last 50 years, that beige line has moved further and further south. It has to go a long way. We have to have a very substantial warming before we get anywhere near the major ice shelves of the Ronnie Filchner. And that's an important point to make. The bulk of the Antarctic ice is well below 0 degrees centigrade, and so is still, if you like, secure and safe. It just gives you a few statistics on collapsed ice shelves. Now, ice shelves float anyway, so they've already done their Archimedean bit by raising sea level. But it has been speculated prior to these collapses that they may hold back the flow of the glaciers that feed them. These little arrows here show that when Larsen A collapsed, the feed glaciers speeded up by about a factor 3. When Larsen B went, there was somewhere between a 2 and 6 times acceleration of the glaciers. But the glaciers south of the collapse area, where we've still got bits of the Larsen B left, haven't changed. So nature's done a very convenient experiment for us and demonstrated what people were speculating about, because the models, I'm afraid, aren't up to allowing us to predict exactly what would happen with any confidence, that if you remove ice shelves, the glaciers accelerate, and of course in doing so, they do increase their contribution to mean sea level rise. And overall, it looks like the peninsula is adding about 10% of the annual mean sea level rise that we see today, and that has increased as a result of these ice shelf losses. Looking at the Antarctic more generally, this is the Kurt Davis et al. Data from Altimetry using ERS and other altimetry over a decade or so. The hole in the middle is because the altimeters that these data are drawn from don't get further south than that. You can see over the bulk of what's called East Antarctica, the yellow and orangey regions, because a warmer atmosphere carries more moisture, there is more snowfall. That was expected. You can see that there's considerably more snowfall at the root of the peninsula, but you can also see some blue areas where there's some very, very substantial discharge. And in particular, if I just summarize that, so there's growth in the East Antarctic. There are major discharges on Pine Island and Thwaites in the Amundsen Sea embayment, which is on the left there. I'll show you an arrow in that. And then there are 1 or 2 areas in East Antarctica which are showing the same sort of behavior. So that area with the purple star on it is particularly important, but there are a couple of others that we need to keep an eye on too. Now, why are we interested in these? Well, 50 years ago, Mercer suggested that these marine ice sheets, in other words, ice sheets that sit on rock below sea level, and in some cases 2 kilometers below sea level, might be unstable to warming. Actually, it'll be an ocean warming, not an atmospheric warming. And that there could be some runaway positive feedback that once these things started to slide would allow pretty rapid disintegration. And really, on the basis of no evidence, that hypothesis came in and then went out of favor. But it's been revived by these satellite data, altimeter data, that show that it's indeed the marine bits of the ice sheet that seem to be doing something. Now, these are in areas where the air temperatures are very low, so the candidate for change here has to be changes in oceanography. We know that between the last glacial and the Holocene, sea level rise has run at rates at least an order of magnitude greater than those that we see today. So we know that when ice sheets go, they can go quite quickly. And just to remind you that there was 120 meters of sea level rise over that period. But I've filched this very nice little overhead from Bob Binshadler, who showed it at the Antarctic Treaty Meetings in Edinburgh last week. This is a comparison of the Vostok record of temperature running from left to right over the last 400,000 years, and a record of mean sea level rise. And to guide the eye, if I can put that in, Bob makes the important point that although latent heat diffusion of ice is or snow is whatever it is, initially it's not obvious that there might be an asymmetry between making ice and melting ice. It seems that on the planet, that's not the case. That is that if you go to a warmer world, ice melts and sea level rises much faster than it falls. And if you think of it, it's because gravity helps. When you're building an ice sheet, gravity is trying to cause it to collapse. When you're melting an ice sheet, gravity is very much helping it to collapse. So on these sorts of timescales in a warmer world, you will inevitably end up with less ice and higher sea levels. So, recognizing that time is running short, just draw your attention to the fact that at the southern end of this circulation system, there are some regions of deep bottom water formation. I'm not going to spend any time on this because I know that Keith and others will take you through it, but there are some very specific mechanisms in the Antarctic to do with the production of sea ice and the drawing of warm water in under the sea ice as the dominant winds generate ice in these shore-based ice factories, reject salt and produce dense water that tips off into the abyss. But it's not just under the sea ice, it's under the ice shelves that important things happen. So if we zoom in, again, I'm not going to talk about the processes because there are others here who can do it much better than I can, but there are some very important and quite complex processes that take place under ice shelves, generating deep bottom water that goes off and chills 40% of the world ocean, but also causing rapid melting at the grounding line, which is pertinent to whether Mercer was right or wrong. And here's an Antarctocentric view of the global circulation system, which just shows the third dimension of depth and indicates the importance to the world ocean of the Antarctic refrigerator, as well as the North Atlantic refrigerator, for keeping it the way it is. And of course, any changes in behavior of those processes will have global consequences. So I'm getting towards the end of my pitch. The global consequences of regional polar warming are all to do with sea level rise, global ocean change, and the coupled impact on the atmosphere and climate. And indeed, if one looks at John Schellenhuber and others' so-called tipping point diagram, which is intended to show places in the Earth system which are vulnerable to internal dynamics taking over from an external tipping force, one finds that they've identified, I can't remember how many it is, what is it, a dozen or so potential tipping points in the Earth system, and it's no surprise to me that a number of these relate to polar processes. Right, what do you need to do to make progress in studying these processes? Well, if you want to look at the history of them, where the ice sheets were and where they flowed in the past, if you want to understand what the oceanography is now, if you want to understand what is happening to the ice sheet, its grounding line and its ice shelves now, if you want to understand what's happening to the sea ice, and if you want to understand what's happening to the biology, then you need to get into this hidden zone underneath the sea ice, which is underneath the ice or ice shelves, which is either very difficult to access if it's sea ice, or essentially impossible to access other than by drilling holes through the ice shelves when we're talking about ice shelves. So what lies beneath is the big issue, and this beast provides the UK community with a superb way of finding out. So Autosub Under Ice addresses key issues important to all of these major Earth system science questions. Here's a picture of the Ronnie Filchner ice shelf, this area which at present is well outside the range where we might expect collapse, but where there are important processes taking place beneath it as tides and currents squish water into this cavity. The red dots show areas where Keith and others from BAS have drilled their way through the ice shelf to put instruments in at a point to try and figure out what's going on down there and then model it. The proposal with this beast was to get right underneath to some of the places where those key processes I was telling you about take place. It was only partially pulled off this time, but clearly the demonstration of the technical capability convinces that with a little bit more effort and perhaps a slight tinge of additional luck, this will soon be something which is meat and drink to the community trying to understand those processes. So I mentioned the International Polar Year, which kicks off at the beginning of next year. The Autosub continues into the future. Hopefully it will be part of the great campaign to understand the polar regions better that will run from 1st of March 2007 to 1st of March 2009. IPY intends to lead a legacy of new instrumentation, new networks, which allow the polar regions to be monitored even more intensively in the future than in the past, and Autosub surely will play a role in that. And with that, people always ask me, have you got penguins in your talk? And so I always have to finish on this one. So yes, I have. So thanks very much.